Hello. So this is chapter 8, section 2, the surface area. In our early videos, we discussed surface area case 1. So today we're going to go to case 2. So case 2. So this time, for case 2, we are given a curve that is given as x equals as x as a function of y, and the interval in terms of y also, but still the rotation is about the x-axis. So this curve is x equals f of y. It's a function of y, and so the rotation is still with respect to the x-axis. So that makes y to be the radius of the circle, and the arc length is still dl, but yet the interval is given in terms of the y variable. So we want to find when we're going to rotate this arc with respect to the x-axis is going to generate a surface, and the question is, what is the area of that surface of rotation? So it doesn't matter. dl is still 1 plus f prime of y square under the square root of, so 1 plus, so the square root of 1 plus f prime of y square dy. This is like case 2 of the arc length. So ds, the surface area element is usually 2 pi times y times dl. We put y here because this y is positive, so we didn't need to put the absolute value. So after we replace dl by square root of 1 plus f prime of y squared dy, then we can integrate. Notice that everything here is in terms of y already. You have y. So you want to, so we integrate in respect to y. We're going to integrate from c to d. The y boundaries are already given to us. Y is between c and d. So but this 2 pi y, okay, because the rotation is, as we said, when the rotation is with respect to the x-axis, the circumference is 2 pi times y. So here we keep 2 pi y, and then times the arc length element, which is in terms of y. So therefore the integral is going to be from c to d. That's where the given interval is that y is between c and d. So here's an example. Find the area of the surface obtained by rotating the curve x equals 1 plus 2y squared, and y is between 1 and 2 about the x-axis. So when you, let's just put the formula next, so we know this is the formula. Well, actually it's written here. So this doesn't change, 2 pi y. C is 1, D is 2, so the integral is going to be for 1 to 2. So what we need here is the derivative of f of y. F of y is given as 1 plus 2y squared. So when you take the derivative of 1 plus 2y squared, you get 4y. When you square it, you get 16y squared. You plug this into here, you get 1 plus 16y squared under the square root. So it goes here. And so 2 pi y times square root of 1 plus 16y squared, and then you integrate from 1 to 2. But this again, it's a u substitution problem because you have y here. So when you set this to be u, then when you differentiate y squared, it's going to give you y dy. So we let u be 1 plus 16y squared, du is going to be 32y dy, and then we solve for y dy by dividing this equation by 32. So you get du over 32 is y dy. Now I want to change everything also I'm going to go and change the limit of integration. So when y is 1, u is going to be basically 17. When y is 2, so we plug in 2 for y into here, we get u to be 65. So when we go from y integral to u integral, we're going to have a 2 pi times y. So what is y? Okay. So y dy is du over 32. So we have 2 pi. Going to bring 2 pi outside. Actually, so it's going to clearly given here. Now the limit of integration is going to be from 17 to 65. So we get the u integral. We're going to bring one of the 32 outside because it's a constant, and then we integrate the u to 1/2, which is u to 3/2 over 3/2. Divide by 3/2, flip, becomes 2 over 3. Here we simplify 2 to get pi over 16, and then another 2 to get pi over 8. 8 times 3 is 24. Get pi over 24. Evaluate u to 3/2 at 65 and at 17, and then take the difference, and then you get the surface area. So for case 3, so this time they give us the curve y equals f of x. They give you the interval, the x interval, x is between a and b, and the rotation this time is about the y-axis. Okay, not the x-axis, the y-axis. We know when the rotation is about the y-axis, then the circumference is going to be 2 pi times x, because x is the radius. We put the absolute value just in case when x is negative. And the arc length is still the square root of 1 plus f prime of x squared dx. So that's the arc length element. Since the x is between a and b, so we know we're going to integrate from a to b. So that's the formula for case 3. For example, and then case 4, I went to case 4, but I will explain. So for case 4, we have, at this time, you are given a curve as a function of y. The interval is given as a function of y, and the rotation is about the y-axis. Because the rotation is about the y-axis, you're going to still have a 2 pi times absolute value of x. But then the arc length element is, since they gave us the coordinates, the interval in terms of y, so the arc length element is going to be square root of 1 plus f prime of y squared dy. We integrate from c to d. So this is a case where this x will be replaced by f of y, so that everything is consistent in terms of y. So that's case 4. Okay, so let's go to let's look at this example. They give us the curve, which is y equals cube root of x. They give us the interval, y interval, so y is between 1 and 2, and the rotation is about the y-axis. They ask us to find the surface area of rotation. So let's do case 4. Okay. So case 4 basically says they give us x equals f of y, okay. So, and they give us the boundary in terms of y, and the rotation is about the y-axis. So we need to change this. We're going to change this in terms of x as a function of y, okay, not y as a function of x. To change it, we're going to cube both sides. So you get x equals y cubed. Okay, and then the boundaries are already the y boundaries. C is 1, D is 2. The rotation is about the y-axis. So we know the formula is 2 pi x here. And then you have the arc length in terms of y. So f of y is y cubed. So y cubed would be
differentiate it here, and then square. We integrating with respect to y, so we cannot have x. X must be replaced by y cubed, because x equals y cubed. So here, x is going to be replaced by y cubed. We're going to integrate it from 1 to 2. So then everything here is in terms of y. So when you differentiate y cubed, you get the 3y squared. When you square it, you get 9y to the 4th. It goes there. So you end up with this integral. As you can see, since you have y to the 4th, when you make this, whatever is under the square root as u, when you differentiate, it's going to bring us y cubed dy. So this is perfect u substitution problem. Okay, so you let u be 1 plus 9 times y to the 4th, and then du is 36y cubed dy. We solve for y cubed dy, we divide both sides by 36, and then we change limit of integration to get when the y is 1, u is 10, when y is 2, u is 145. So we're going to integrate from 10 to 145, 2 pi times square root of u, and then times d over 36. Bring 1 over 2 pi over 36 outside because they're numbers. Integrate u to 1 4, u raised to a half, and then plug in 144 and 10, and then take the difference, and then we get the answer. But the point is that the same problem can also be solved using case 3. Case 3, we keep it as a function of x, and then we change the interval, the y interval in terms of x interval. So we say when y is 1, what is x equals to? So we solve this equation, we get when y is 1, x is 1. When y is 2, you get x equals 8. So the interval 1 less than equals y less than equals 2, in terms of x is 1 less than equals x is less than equals 8. So case 3 says take 2 pi times x and then times the length, the arc length elements. So we're going to integrate from 1 to 8 of 2 pi x times. Now f of x is a cube root of x. So to differentiate the cube root of x, we change it to x raised to a half. We differentiate, and then when we square, we get 1 over 9 times x raised to negative 4 over 3. And then we this is kind of messy because comparing to case 4, this becomes a little bit harder. So since we have this, you kind of find the common denominator and then change the exponent from negative to positive, and you end up with square root of 9 times x to raised to 4 over 3 plus 1, all divided by 3x to 2/3. I think it's done here. The whole process is done over here. So the last result is copied here. So then so that goes here, and then 2 pi times x. Then you can simplify x with x to 2/3, which give us x raised to 1 over 3. And then again, this is a u substitution. When you let that to the u, and then du give us x to 1/3 dx. Then times 12, divide both sides by 12, you get x raised to 1 over 3 dx. And again, you change the limit of integration from x to u. So when x is 1, u is 10. When x is 8, u is 144. Now that kind of remind you what you just did. So you get this is the u integral. So again, you bring 1 over 12 and then 1 over 3 outside, and then 2 pi, and then simplify, and then you integrate the square root of u. You end up with this because we already did this. So you give us exactly the same answer, but the same problem we did it 2 ways, case 3 and then case 4. And we know case 4 was a little bit easier, but we get the same answer. So this answer is exactly the same, that we got over here when we did case 4. Okay, so that's where this video ends. Thank you very much.